Okay, well, it is 12:30, so I think we can get going. And I'm going to give a very brief introduction to Raquel, and then I will turn it over for a more full introduction to Krzysztof Czarnecki, who's a professor in electrical and computer engineering, and cross-pointed in computer science. And I've known Raquel for 25 years or quite a long time. We were postdocs together at U of T, and she has blown me away in her success. And so I'm really, really happy to have Raquel here to talk to us today about her pioneering work in machine learning. And so I'm going to turn it over to Krzysztof, who will go through some of Raquel's achievements. So,
all right. Thank you. So it's a absolutely great honor for me to introduce Raquel. Although she probably doesn't need an introduction from most of you, and it's a challenge to summarize all the vast and trailblazing body of work and her achievements, and still leave enough time for her talks. I'll try to be brief. So she started her academic journey at the Universidad Pública de Navarra in Spain. She received her PhD from EPFL in Switzerland. She did postdoc at MIT in Berkeley. And currently she's a professor in computer science at the University of Toronto, a founder and CEO of Wabi Innovation and co-founder of the Vector Institute for AI. And so her work spans both fundamental contributions to machine learning, including things like deep structured models and the concept of empirical fields in CNNs. And in robotics, she covers pretty much the full pipeline, including perception, prediction, planning, and simulation. And so most importantly, she has been a trailblazer in creating the foundations for a new and sort of third generation of self-driving car technology, which she refers to as AI first approach. She's been working on that for at least 4 years, roughly when her Fast and Furious paper on end-to-end prediction and tracking came out. And I see that the research field and industry are clearly headed in the same direction, but Raquel is already ahead of everyone else. And so from 2017 until last year, she was the chief scientist and head of R&D at Uber ATG. And so that's where her approach that she's been spearheading has taken much more concrete shape. And so literally, she's got a jaw-dropping research output, like when you look at last year, this year, and not just in volume, but simply fascinating ideas and results. And I have to say that looking at her Google Scholar page can be absolutely humbling for an academic. So I learned only this year there's 8 CVPR papers, 15 patent disclosures, and most importantly, amazing ideas like the MP3 paper on unified mapping, perception, prediction, and planning, and entirely new way to do simulation using pre-recorded sensor data, and so on. So the challenge of self-driving has proven to be incredibly hard problem, harder than most companies initially thought, including Uber. And so since leaving Uber ATG, she has now gets a chance to implement her vision at Wabi, her own startup, for which she managed to raise roughly 100 million Canadian in a matter of months. So really, when you look at all of that, it's I would say for Raquel, the sky is the limit. And so we're incredibly lucky to have her here in Canada, and also now with us for this talk. And so I'm excited to hear about the latest evolution of Raquel's vision. And so I'm sure so you are. So logistical point, there is a chat, and the idea is to collect your questions as they pop to your mind during the talk. And so at the end of the talk, we're hoping to have 10, 15 minutes for questions, and we're trying to wrap it up within 1 hour. So I'm going to stop here, and so Raquel, the virtual floor is yours.
Thanks, Krzysztof, for a really, really kind introduction. So I think you really managed to put me as real as it could be. So thanks for your really kind words, coming from somebody I really respect. Cool. Very excited to be here today, talking about, what I think, is and should be self-driving 2.0, and in particular, an AI-first approach to self-driving. And without further ado, let's go into the details. So I think, one of the things that, we should start by mentioning is that self-driving is really one of the most exciting and important technologies of, our generation, or even, this century, right? In the sense that it's a very, very challenging problem, but also it's a problem that is going to transform the world as we know it today, from things like requiring much less parking spaces, to less congestion, to improve safety, right? There's 2 million people that die every year on the road, et cetera, et cetera, et cetera. Some of these, big advantages of this technology. And, for me, it's really my life mission to solve self-driving, and, working really hard to make sure that this actually happens soon. So I'm going to start the talk today by giving maybe a 30 seconds introduction on how self-driving works, okay? And then we are going to go over developing a small, simple model, and we will go into more and more levels of complexity, okay? And then we will add, all sorts of interesting things to it, and I will finish with kind of simulation. But, if you look at, how typically a self-driving software stack works, is that first the self-driving vehicle senses the environment. So I'm showing you here with the LiDAR point cloud at the scene from the top, right? And the first thing that a vehicle typically does is that it basically localizes where it is in the world with precision of a few centimeters. And the reason it does this is so that it can exploit high definition maps, which are preloaded on the vehicle, and really gives a lot of information about where are the lanes, the intersections, the traffic lights, the rules of certain places, etc. So there is a lot of prior knowledge that gets encoded into these maps. Then once the vehicle knows where it is and it has the maps, the next thing that it needs to do is to perceive the world around it. And this is both the categories of interest, such as pedestrian, cyclists, as well as all the stuff that is around the vehicle, potentially debris and other things like this. But understanding sort of like the past and the present is not sufficient. In order to plan a safe maneuver, the vehicle has to also predict into the future how the different actors are going to be moving. And this is actually a pretty hard task that is called prediction in the self-driving community, and it's called, I guess, motion forecasting in the more research community. And basically, given sort of your understanding of the past, the present, and the future, then the vehicle, sort of looks around and decides into what is a safe maneuver to execute, such that we can go comfortably and safely towards the goal. And this process is typically repeated every fraction of a second, typically 100 milliseconds, which is the frequency of the LiDAR. Okay, this is in a nutshell how almost every self-driving vehicle stack works. Now, if we look at, we step back and then think about, where is self-driving today? So we've seen, meaningful progress since, the DARPA Day Challenge, the DARPA Challenge days, which is, 17 years ago now. But when you look at commercial deployment of this technology, it's really very, very limited, right? We see it in very small operation domains that are also very, very simple. So this promise of self-driving at the scale that you hear in this industry over the past couple of years is not there yet. And the question is, why is this the case? What's, making the industry not progress as fast as it should be? Well, I think it's important to know that the problem is very hard. And maybe it's harder than people, used to acknowledge it is. And, why is it hard? Well, first, if you think about the task of driving, actually, it requires very complex and nuanced, decision-making, right? Small changes of the inputs might result in very different maneuvers, right? Particularly when they're safety critical. And that's actually hard to do. Now, what makes it also very difficult is that the scene in front of you can vary a lot, So there is, billions, trillions, whatever, ways that scene can be represented in front of you and how we can enroll. Right, so you need to be able to handle all these different situations, whether it's the weather condition, the actions of the different actors, how they look, et cetera, right? You need to be able to handle all those variations. And the thing that makes it even harder is the fact that, there are things that happen a lot, but there are many, many things that happen very, very rarely, right? And we need to be able to handle those and even understand that we can handle those. And that makes the problem extremely hard, right? All these long tails, as is typically talk about, of the distribution of all the things that might happen in the world. All right, so this is one of the main problems. The second problem is actually about the solution itself. So not only the problem is hard, but the solution is actually, or the current solutions are what I call imperfect, or they are not solutions to solve really this at the scale. Right, there is, and if you look at, you dig deeper into the software stacks, there is not that much change or evolution since the DARPA challenge in 2004. The core components look relatively similar, right? And, yes, there is AI here and there, but it still is something that hasn't really evolved into a fundamental different technology. And the way that I typically describe, how the industry works or what we see is that, they decompose the problem into a lot of small sub-problems, and then you start to try to build it bottoms up. So it's like, the analogy will be that, like trying to build a puzzle by building every single piece individually and hoping that it fits together nicely. This is very, very difficult to do. So the current approaches rely really on manual tuning. They're too expensive. They don't scale. They are overfit to very small operation domains. If you go a couple of streets to the right, it's not going to work, right? So this is not good. So let me go maybe dig a little bit deeper into, more specifically, what are some of those challenges for the industry? So most of the competitors work on or have a software stack of what I call the traditional software stack, okay, which is very kind of robotic centric. And the problem with this is that, well, first of all, as I mentioned, that they decompose the problem into small subproblems, and then teams work in these small silos, trying to build solutions for these individual pieces. And then, as I said, there is no holistic kind of view, and then hope that that will actually solve the entire system. And it's very, very hard to come with optimal solutions or great solutions that way. Also, if you look at, I talked before about perception, prediction, motion planning. If you look at the interfaces between these models that get executed one at a time, it's very, very small. Maybe you pass vehicle trajectories as well as maybe some notion of uncertainty. But by the time you go, to your decision-making process, you have lost almost all information, right? And you have to do, more and more complex decisions with less and less information. You go more and more blind, right? So this is sort of the opposite of what you would like to be, right? So this is problematic. And if you have any mistakes, this is going to cascade, and it's going to be impossible for you to recover. On top of this, if you see the development in the industry, then you will have, fleets of self-driving vehicles driving around. They identify types of failures. And then given this type of failure, what they do is they don't change the overall system. What they do is that they build yet another model to try to tackle this one specific thing. So at the end of the day, the software stack looks more like an expert system composed of, hundreds of these models. And by hand, they're trying to combine this into a decision-making process. So that doesn't scale. That's too brittle and requires too many people to tune and maintain all these models. And lastly is that, there is no automation in this process. Basically, every time an engineer or a researcher makes a change, this is going to affect everything else. So you need to go model by model, making, retuning the entire system. So as a consequence, every single, kind of change, even if it's very small, typically takes a quarter, 2 quarters to actually land in production. And this is why progress is very, very, very slow. Okay, so an alternative, right, is to say, well, why, it's the boom of AI, why don't we just use AI to solve this, right? So there's been a couple of attempts to try to say, okay, we'll have a neural network that take in, maps and sensor data as inputs, basically will spit out, STN command and acceleration such that, it can drive the vehicle. The problem with this is that, well, it's actually, this is treating the AI system as a black box. If it does mistakes, it's really, really hard to understand why and what to change, what to do. And it relies on having a lot of data. And a lot of data is actually problematic in this case, because in order to handle safety critical cases, we need examples of safety critical cases, which is unethical to collect this in the real world, right? So we need a different solution. Also, this is not interpretable, so regulators definitely don't like this kind of approach. And sorry, my computer froze. Let's hope that. Oh. All right, cool. And so I believe really that there is a need for something different, a different or better way to move forward. And in particular, I believe there is a need for new type of technology, what I call self-driving 2.0, which is sort of enhance the advantages of these two types of approaches, but without having their disadvantage. And this is what I'm going to be talking about today, particularly Waabi's approach, which is different approach to try to solve self-driving. And the other thing that I think is worth mentioning is that it's not just about we need new technology. The other thing that is important is we need a new approach to develop this technology in terms of our team composition and how teams work. And in particular, we see in the industry a lot of consolidation, where everybody hires everybody from everywhere else and everybody's converging to the same software stack. And this is very problematic, because if you don't have the solution to this problem and everybody's thinking the same way, it's going to be really, really hard to find the solution, right? So I believe that we need diverse perspectives in order to come up with much better solutions. And in order to have diverse perspectives, we shouldn't be all looking the same, right? We all should have different backgrounds and different ways of really approaching and thinking about the problem. And that's the way that we challenge each other and we build better technology. This is something that we are used to in research. It's much less frequent in companies and in engineering. Okay, but it's extremely, extremely important for this technology. Okay, so we need diverse teams that build diverse set of approaches that also sort of represent the diversity of people that are going to use this technology. All right, so now the question is, what is our different way of trying to build this tech, or what does it look like? So it's going to be a single AI system. So it's going to be an AI first approach, integrated approach. And this has multiple advantages. And in particular, the kind of technology that we are building is end-to-end trainable, meaning that the system can adjust itself automatically from data. And this enables you to do a couple of things. First is that you can actually utilize more complex functions to solve these individual subtasks. And these more complex functions can even access raw sensor data along the way. So you don't have this cascade of mistakes. You don't rely on a few parameters that humans can tune. You have a family of solutions that is much bigger than if it's just humans trying to do this. At the same time, you get the automation. So every time that you make a change, automatically it's gonna, retune everything. So you don't have this process of landing something that takes, 1 quarter, 2 quarters. Now you are in, 1 day kind of framework. At the same time, our technology is not just a straight up neural net that does everything, as a black box. It actually creates interpretable intermediate representations, and you can really incorporate your prior knowledge into the model, which is something, great about self-driving is that we know a lot about the task. So we should build models that understand that already, and they don't need to learn everything from scratch. And as I said, this is interpretable, and, it's technology that can be, verified for safety, for example, much easier. This approach is much more scalable. Also, in particular, we have a new generation of algorithms that combine deep learning, probabilistic inference, and complex optimization, right? I call these deep structure models many years ago. So these are, generations of this technology. It's very, very powerful approach. And it's much more scalable in the sense that it generalizes much better. and you can actually utilize or generalize across sensor configurations, geographies, etc. And it's much more affordable. In the industry, because of the complexity of the software stack and all these models and whatnot, you need, a couple of thousands of engineers, right? I don't think that this is necessary. Here you can do with much less, okay? And in particular, the other piece of the puzzle is that, so we have, this differentiator, which is our AI first approach. And the second piece of the puzzle is actually the simulator. So there's been, some talk in the industry about simulation, but not to the level of really the importance that simulation actually has. And in particular, the current simulation approaches are really in the baby steps. We need something that is much more sophisticated. And, in particular, you need a closed loop simulator that can really test and execute, what the vehicle will have done, but in a way that you need to regenerate how the vehicle will have observed the scene, right, with sensor simulation, so that you can actually really test the entire software stack. And you can do this at scale, also automatically. Okay, and I will tell you, quite a bit at the end of the talk about this, but this is the second really key differentiator that is very, very important and something that is absolutely needed for getting to self-driving at the scale and to really verify these systems. All right, so the agenda for today is actually quite ambitious. I have a lot of stuff to show you in autonomy. And as I mentioned, we're gonna go step by step so that you kind of see the process of building this technology from something simple to incorporating more and more stuff. And then at the end, I hope I have time to show you some stuff on the simulator. We haven't yet unveiled Waabi's technology, so I'm gonna show you previous generations, okay? But you're gonna get a sense of, what we are building is really the next thing, is, the next thing on steroids, but you can get a sense of basically where we are going, okay? Cool. All right, so without further ado then, let's go into talking about autonomy. And remember, autonomy is building the brain of the self-driving car or vehicle. All right, so the, traditionally, right, as I mentioned, the people build these models one at a time and they're independently modeled and whatnot. So what we're gonna do is we're gonna start by unifying more and more such that we have at the end this single AI system, okay? So let's start by trying to build a model where we're gonna do perception as well as motion forecasting, so detect where everybody is in the scene and predict where they're gonna be going within a single network, okay, a single AI system. And let's see how we can actually do this. So and we're gonna do this obviously with deep learning, with AI, okay? So the input is gonna be, your favorite sensor. Let's start with the LiDAR, right? And in this case, it's gonna use the past history of, a few frames of the LiDAR. And we're gonna build a neural network that basically, learns some, good intermediate features such that we can decode into where are the objects in the scene. And simply we can, sorry about that, my computer is not listening to me. And also we can decode not just where the different actors are in the scene, but also we can regress where they're gonna be moving into the future, okay? So this is, the first of its kind system that will actually unify perception and prediction into a single neural net, which resulted in much better performance, can handle much more sophisticated sort of predictions into the future. And you can do this in a few milliseconds on your favorite hardware, okay? And what I'm showing you here is the results. So we're gonna be driving around, in this case, cities, and we're gonna detect all the objects of interest, and we're gonna predict with these dotted things where they're gonna be going in the next second, in this case, okay? So if there's a single point, it means that we predict that they are static. If there's multiple points, we predict that they are dynamic, and how far away they are is basically the velocity that we predict. Okay, so to note is that, as a self-driving vehicle, we need to understand a lot around us, right? There is so many vehicles or actors going around, and we need to predict, as I said, what they're going to be doing. So it's actually a pretty difficult task, as you can imagine. And there's a lot of occlusion and things like this that happen. Cool. So this was sort of like the first system, and it was very, very simple. For those of you that are in machine learning, right? It was treated as a multitask problem, right? You detect and regress, So it's actually pretty easy to train such a system if you have data. And what we're going to go now is that add more and more reasoning to this system. Okay. So the next thing that we're going to do is we're going to look at how we can also incorporate different sensing modalities, right? Because LiDAR is great, but we also have cameras, radar, etc. So we would like to be able to utilize all these sensors. And the way that you can do this with these models is actually also quite natural, is that you can have sort of a way to process, one stream processing, one sensor, another stream processing the other sensor. And what is important is that, you fuse the information, not just at the beginning, not just at the end, you actually learn to fuse along the way this information. And this is a concept that is very, very, very important because, early fusion or just late fusion are definitely suboptimal. And the network can learn a much more sophisticated fusing process if you enable it to fuse all the way, along every single computation. And what is important in these fusion operations, I'm not going to talk about the details, but you can actually exploit the geometric relations between the different sensors. So it's aware of the physics. And that's also very important, is that when you have prior knowledge, you should exploit it in the way that you build your operations, for example. All right, so let's see how this kind of systems actually perform. So here I'm showing you, challenging scenarios, and this is in bird's eye view, so view from the top. This is in camera view. And I'm showing you now multiple, being able to do multiple classes, right? And the thing to note is that, the sensor data is far from being perfect, right? There is like grain in this case, which is going to create, missing data, and the LiDAR is going to create, all sorts of, disturbances on the image space, etc. And you need to be able to handle all these situations. There is going to be some snow cases in a second as well, right? And this is why it's hard to engineer this, right? You need to really learn from data to actually perform this task. So that's what the concept of learning is actually really, really important. All right. Then we're going to go one more level of sophistication, right? Is that, okay, now we were predicting short trajectories of how the different actors are going to behave in the future, but we would like to have a more semantic understanding, right? Which is important for maybe potentially motion planning, which is, can we actually estimate the intention on the different actors? And the way that we're going to do this is very simply, is that we're going to extend our multitask kind of approach to not only detect and track, and regress over the future, but also to be predicting intentions. Okay, and we can do things like condition on the intention. You can actually predict certain trajectories. And the other thing that we are going to do is that in the way that we fuse information, we're also going to exploit maps. Right? If your vehicle is localized, maps gives you a lot of information that will make you, have better perception and prediction, right? Because people typically follow the lanes, respect the rules of traffic, etc. Okay, so similar idea. We can also have an additional stream, processing the maps and then fusing the information. Now I showed you how to do images and things like this, how to fuse. From now on, to simplify my drawings, I'm gonna just talk about LiDAR, but obviously you can generalize this to use any sensor information all together and fuse, okay? Cool, so let's see how this works if we add now reasoning about intention. So what we get for free now is that we have a probability distribution over those intentions, and we have multimodality. And what I want you to focus on, there is a lot in the plot here, but I want you to focus on the bottom here. Okay, and in particular, what you're going to see here is that the color represents certain intentions, and the arrows also represent some other type of intentions. Okay, so the more red it is, the higher the probability of being stopped. The more purple it is, the higher the probability of being parked. So these two things are very similar concepts, but the semantics are very different. And the reason why we want to distinguish is that what the self-driving car will do will vary whether the car is just parked or whether you're just waiting, for example, at the intersection, right? Typically, you will change lanes or not depending on which one of these cases it is. And the arrows that you were seeing are basically representing whether we are turning, we're continuing straight, or we are basically changing lanes. Okay, so that's basically a way to not only detect all the objects of interest, but now have more sophisticated prediction that a motion planner can use. And what helps you in this process is that, well, when we drive, we actually signal oftentimes our intention. And this is quite interesting, right? Because we typically put the turn signals in order to say that we're going to take a turn, for example, or we're going to change lanes, right? So we can have networks that also look at spatiotemporal videos, right? Once you detect where the objects are, and then reason about which turn signal is on. And this is what you're seeing with the green arrows. This is the right turn signal on. The other arrow is the left turn signal on. Both on will be both are on, and nothing will mean that there is nothing there. Okay. And if you look at what the network is actually looking at, it's quite interesting because this is unsupervised. It learns to look at things like areas of high reflectivity, which are where potentially the turn signals are located. And this is quite interesting because different vehicles have very different turn signals. And here we have never labeled the location of a turn signal ever. Okay, so this is weakly supervised. We only say left on, right on, nothing on. And it uses a very small amount of data to train this. Okay, so you can exploit this information. Now you need to be careful because not always humans signal, and sometimes humans signal things that they don't do. You get distracted and you left your right turn signal on. That happens a lot, right? You have your music, whatever. So you need to be robust to the fact that what you observe is not necessarily what the intention is. Cool. So now let's continue building on this prediction of really understanding the future, right? And as I was mentioning before, the future is actually multimodal, right? In the sense that, we don't necessarily understand what everybody's intention is. In particular, for example, as we see a vehicle at an intersection, we don't know whether they want to turn or they want to continue straight, right? So this actually makes the possible realization of the future by definition to be something uncertain, something that has multiple solutions, right? So we need to build prediction systems and motion forecasting systems that build probability distributions over all these different modes. And then we need a motion planner that is able to take this into account when planning a safe maneuver. And this is actually extremely hard. What makes things even worse is the fact that, well, vehicles don't act independently. They actually react to each other, right? So you need to take into account all these dependencies when you make your predictions. And you cannot go maybe too fancy in the way that you model these things because you need to, this is a safety critical system in the sense that it needs to make a decision in real time, right? So there is a constraint in terms of, how much computation you can do. So you need to be very, very clever in terms of how do you use your computational budget. So this makes, as you can imagine, right, this task, very, very difficult. So what people have done or what you see in the literature about handling multimodal distributions is that they typically model the marginal distribution with multiple modes. The marginal meaning the probability distribution of every actor. And yes, when you compute that marginal distribution, you take into account the dependencies between the different actors. But at the end of the day, your output is a marginal distribution that you move or you pass to motion planning, and this is actually problematic. Okay, but the kind of representations they use is we use a lot of occupancy representations. Some of the folks like Waymo like a mixture of Gaussians. We also like a lot non-parametric distributions, right? Because they're very flexible. Non-parametric means you have a set of trajectories, whatever that set is, and you can cost them. And some folks use autoregressive models, but they are typically too expensive to run. Okay, but as I was saying before, well, modeling this marginal distribution is actually something that is not going to allow you to do good motion planning. Why is it the case? Because if you look at, the marginal distribution of this vehicle, the marginal distribution of this vehicle, it has multiple modes. And then now the self-driving car has to somehow take those modes and compose into a final decision. So it's going to do the cross product of all the modes. So you have missed all the information about the fact that really there is only like two possibilities typically in this case, right? Collisions are not frequent. And these two possibilities are that they are going to slow down and therefore I go, or they decide to go and therefore I should slow down, right? And this is lost if you just model these marginals. All right, so let's try to build a model that actually can reason about these multimodal distributions, but taking into account all these correlations in a way that when it generates samples, it generates the entire scene at once, okay? Instead of building these marginals. So how are we gonna do this? We are also gonna change a little bit the perception system to do something a bit more sophisticated, okay? So we have our LiDAR data, we have our map data, we're gonna process it, we have some nice representations, intermediate representations, we can extract and detect the objects of interest, right? And in this case, we're gonna do what is called a two-stage detector, where basically we can detect and then refine. And then we have for every actor, a complex representation that is coming from a oriented crop in the region of interest. Okay? And this basically gives us some representation for every actor that we have detected in the scene. And then the question is, given this representation, how we can now reason about what they're going to be doing. Doing in the future. So there's a lot going on in this slide, but the important thing here is the fact that we're going to build what we call an implicit latent variable model, which is basically going to take into account, all these dependencies, and it's going to do it via graph neural networks, which is, a generalization of, some type of neural networks that are very amenable to variable number of inputs in this case. Okay, and why do we need variable number of inputs? Is because we have different actors, and every scene will have a different number. It's not that it's a constant number. Okay, so this is a very nice way to actually, sort of combine the information through message passing between the different actors. All right, so this is a model. So we have an encoder that is a graph neural network. We have a decoder that is a graph neural network, and it's a very natural way to model. And the latent variable represents the entire scene. Okay, and then we can decode from this latent variable. So how will inference work in this model? It's going to be that we're going to detect, compute the feature representations. Then we're going to sample from the prior distribution and using the condition on the input, right? And then basically we're going to decode to have the final answer. And every time that we decode, we have an entire realization of the scene. We can sample multiple ways, and then we get multiple realizations. This is how we get our different modes of the distribution. Okay. So it's a very, very simple process. You can do this super fast. Okay, so it looks very complicated, but actually you can still do it within real time. And what is interesting with this latent variable model is that, what I'm doing here is I'm taking two values of this latent variable and I'm interpolating in between. And then you see that by moving that, I actually get different explanations of the entire scene. And in a way that makes sense, right? You see that either the traffic is decided to go or the traffic is decided to stay, right? As we go in different modes of this. And the other thing that is interesting is, without the details, is that we can train the system end to end just by having explanations or having training data that has the realizations of the future. Okay, which you can do just by labeling bounding boxes in videos. Cool. So this type of model actually works remarkably well. So this is kind of the state of the art, and this is the model I just talked about, where in terms of reconstruction, how well it mimics what humans do is actually much better. But what is important is that it predicts really consistent estimates, meaning that our predictions, even though they're multimodal, result in no collisions, versus the other models have explanations that actually collide in the future. And this is the model, basically just working as it does inference. And then you can see that, it does very sophisticated perception as well as prediction. And when it's required, it uses, it has like multimodal distributions, right? As you will see in some of these examples, for example, whether it turns versus not. And it's something that captures very, very naturally. You don't need to say, how many models you need in your model. Cool. So we build now a sophisticated prediction system, right? It's end-to-end from raw sensor data all the way to prediction. And what was interesting about the system, right, is that it took into account all the dependencies between all the different actors in order to predict what they're going to be doing in the future. Now, if we look at what we have done so far, everything that we've done is really conditioned on, how well it works is conditioned on how good the sensor data is. And the problem with this is the fact that, well, if you look at, your scenes as you're going to be driving around, there is some cases where, things that are nearby, you have a lot of observations, so it's easy to detect things and predict. Some things that are far away, it's actually pretty hard because you don't have much observations. But you can argue maybe it's too far, so it's okay. But also you have occlusion, right? And if you have something nearby the vehicle that is occluded, imagine it's a child, right, with a ball, and it's going to appear, it's going to slide, appear just in front of the self-driving vehicle. You need to very quickly understand that there's something there and react accordingly, even though you might actually not see. So you're really limited by what you see. Now, if you think of the future where self-driving vehicles are going to be everywhere, right? For example, say you have multiple self-driving vehicles in the scene, what you can actually do is that you can utilize vehicle-to-vehicle communication for these vehicles to communicate what they observe. And you can use this to actually see much better in the scene. Okay, so that's the kind of what we're going to go next is how can we build vehicle-to-vehicle communication systems that enable us to do very sophisticated processing without limiting our budget in terms of computation. And this is kind of this is one instantiation of our simulator that we're going to exploit to create data for training and testing this vehicle-to-vehicle communication system. Okay, so what you see here is multiple self-driving vehicles that are in color in the scene. There is other actors that are not self-driving vehicles, right? This is their observations, and we need to design now what information we're going to send and how we're going to use this information. All right, so let's look into it, right? So I have these vehicles in the scene, and the question is, okay, what should I send so that they do the best job at perceiving the world? So probably the first thing that comes to mind to everybody is, well, let's just send the raw sensor data. The advantage of this is that there is no information loss. The disadvantage is that it was really difficult already to process our own sensor data, right? There is a lot of LiDAR points and a lot of camera data, etc. And now I'm going to receive even more data. And maybe I have 10 vehicles in the scene, is 10 times more data. So there is no way I can meet the real-time requirements, right, with this. Furthermore, if I send the raw data, I'm going to take a lot of bandwidth of transmission. So I put a lot of constraints in terms of how I can do vehicle-to-vehicle communication. So this is not the best solution. On the other hand, we can do like the total opposite, which is every vehicle is going to observe the scene, is going to process it into the output of perception and prediction, and then we're going to send that, right? And then somehow we're going to combine that, all the messages received or what they perceive and predict into our final solution. So the problem of this is that there is very limited expressiveness, right? In the sense that we have already made all the decisions almost, right? So there is very little to gain from this. And now the good thing is that it's very compact, right? But we need something that kind of is a trade-off between these two things, right? Can we do something that we maintain all the information, but is cheap to send? And that's basically, we're going to do, as I said, something in between, which is basically we're going to learn representations such that we can encode them super with only a few bits, and they encode all the necessary information for us to be able to do better perception and prediction. Okay, so basically this is now a neural network that is distributed across multiple vehicles, right? So you need to kind of learn what every vehicle does, as well as what it sends and how this information is combined. All right, so pretty interesting kind of generalization. So the way that we're going to do this is the following: is we're going to use this as a distributed computing system. So every vehicle is going to do some computation up to these intermediate representations. Then we are going to compress them, and then we're going to send them to the medium. And then every vehicle is going to decompress the messages, merge it together with their own understanding, right, with their intermediate representations through another graph neural network. And then it's going to use this to basically do perception and prediction. Okay, so now we have, this complex distributed system that where every vehicle has to still do almost the same processing as before. There's very little increment, and we're going to transmit very, very little data, but it is the right data in order to really improve perception. All right, and if you look at, how well this actually does. So this is a function of the number of vehicles in the scene. And in here is actually how well your perception system does in terms of AP, which is the major metric. And this is for the prediction system. This is error. So the lower, the better. So you see that this scales really, really nicely with number of vehicles. The more vehicles you do, the more improvements you have. And for those of you that work in perception, you know that 1% AP is a huge deal. Look at how many percents we are getting here. Right, it's 10%. Right, this is an incredible, improvement if you are to use vehicle-to-vehicle communication. And in prediction, also you get, nice benefits as well. Cool. So we, so far we look at joint perception prediction. We look at, different levels of prediction. And what we're going to do next is we are actually going to add the motion planning as well. Okay, so that we will have an end-to-end system where we have perception, motion forecasting, and motion planning. And I'm going to show you, hopefully I have time, 2 instantiations of this, and then we will go to simulation. Okay. All right, so let's get into it. And here you can use anything that I talked before. Okay, we just build a more and more sophistication in terms of the stack. Cool. So the way that, we're going to build the similar idea as before. And the first version of this is going to be a simple multitask version. And then the second version will be much more sophisticated. So in this case, what we're going to have is, again, the voxelized LiDAR, the map, we're going to compute the features. We're going to decode into doing detection, motion forecasting into the future. And we're also going to predict what is called a cost volume. And this motion planning cost volume is the cost for the self-driving vehicle to be at every position in the space at every point in time into the future. Okay, so this is a 3-dimensional cost volume. Space is 2 dimensions, and time into the future is the 3rd dimension. And this is going to be non-parametric and output by the neural net. And the way that we're going to use this cost volume for planning is also very simple, is that we're going to sample physically realizable trajectories. Then we're going to basically cost every one of these trajectories by indexing in this cost volume, right? So every trajectory is a particular location in a particular point in time in the future, right? And the cost is coming just by accessing the cell in this tensor, right? And then you sum all that, and basically you have the cost of every single trajectory. And then the solution is going to be, sorry, my computer is really playing with it. And the solution is going to be the trajectory that has the minimum cost. Okay, very simple way to actually get motion planning. And these trajectories are physically realizable, so everything could be executed by the self-driving vehicle. All right, so all this is learned automatically from data. And you can basically train the entire system end to end. Cool. So let's see how this works. So it's going to do perception, prediction, as well as motion planning. Okay, so you see perception here, you see the prediction into the future. Now we are doing 3 seconds here. And the cost volume, in order for me to show it to you, is 3-dimensional, but we're going to project it into 2 dimensions. And the color is going to represent time. And the area where there is actual color is basically the high likelihood areas for the planner. Okay, so that you see it's costing everything, okay, but this is just for you to be able to see what the planner is thinking. All right, so you see that it's multimodal. It understands the concept of slowing down for somebody that's changing to our lane. Maybe we want to change lanes, as it's doing here. You can do things like super nudge, which is going on the opposite lane to pass somebody. These very, very sophisticated maneuvers. and only train with a few, from a few examples. So you can actually do like super sophisticated things. So this is actually, the first of this kind of these neuromotion planners that is also interpretable, as you see here. And it's, it was very, very promising. And I guess this is something we did maybe 2 years ago, 2.5 years ago. I'm going to show you one more generation, and then I'm going to go to simulation. Okay. So the next generation, we're going to focus on the fact that so far I've been talking about perception systems that detect objects of interest. And there is actually an issue with this type of systems. And everywhere in the industry, everybody uses detection-based systems. So what's the problem with this? Is that, if you're in a situation where you detect everybody, everything is fine, but a detection model basically only passes as objects things that are above a threshold. And it can basically be the case that maybe one of the vehicles is below the threshold. There is evidence there is something, but it's just below this magical number that if it's below that, we ignore it, right? So what means is that if your perception system is based on detection, and then you pass this to your motion forecasting system, you basically don't know that this thing exists. And as a consequence, you're gonna decide to go, maybe to accelerate to cross the intersection, and you're gonna end up in a collision. So this type of system is not safe. Right? Cool. All right, so the question now is, what can we do to prevent this kind of approach, right, to this kind of failure mode? So what we're gonna do is we're gonna get rid fully of detection. And again, we're gonna have the LiDAR data, the maps, and instead of detecting objects of interest and then sort of reason about what they're gonna be doing, we are gonna basically directly predict some kind of semantic occupancy in the present as well as the future. And this basically, you can think of it as a probability distribution of where objects and their semantic meaning are. Okay, but where low probability things are still encoded, we're not going to ignore them. All right, so, and the way that we can basically do this is, in particular, we use a recurrent network that basically predicts, given the sensor data, predicts the future one step at a time. And this gives you consistency. And now, given this kind of occupancy forecasting, now the question is how we can do motion planning. And here for the motion planner, what we're going to do is that we're going to also incorporate our prior knowledge, not just let it to the neural net to hopefully do the right thing. Okay, that's actually pretty important. So it's going to be a sample-based planner, again, where we're going to sample trajectories, and we're going to cost them and decide of what is the best trajectory. And in terms of the cost, in terms of the sampling, it's going to be intelligent. It's going to use the map and whatnot, and it's going to reason about our intentions. But more importantly, in terms of how we cost these trajectories, it's not going to be fully non-parametric, right? Instead, it's built on our intuitions. For example, we would like to cost more if we go through occupied space, because this is going to end up in collision, right? We want to cost more if we don't, drive comfortably. If we don't, don't follow our routes, if you're far from the center of the road, etc. Okay, this is the kind of cost that you have. So you have a whole bunch of these costs, and basically the way that you decide is that for every trajectory you cost them all, and then you select the one with the minimum cost. Okay, but now our costs are actually a combination of our prior knowledge and learned things. And this is something where you can actually train the entire system end to end, and this is very important because then you get the best kind of perception system for your motion forecasting and motion planning systems. All right, so in terms of how well this actually works, just showing you some metrics. So this is the approach that I was talking about, which is here in basically orange. You see that it's very comfortable. It makes as much progress as everybody else. It imitates the human really well, but it's much, much safer compared to any of the other approaches. Okay, so let me show you some examples of this, and there is going to be a lot in the video, so bear with me. But this is open looped planning in this case, where basically I'm showing the forecast into the future of our occupancies, and the different colors you see here, the semantic meaning of them. Okay, for some of the vehicles, for example, we have all sorts of interesting things such as, is it stationary, is it oncoming traffic, etc. So let me just play the video. So you can see here that it can handle, very small objects. It has multimodal distributions that actually understand semantics. And it does a very, very good job at detecting objects and basically understanding sort of their potential intention into the future. And in this video shows that it can handle, as I said, very small objects, be super precise in the predictions, actually matching really well what happened in the future. And it predicts really nicely how the interactions between the different actors. For example, we're going to slow down to make sure we don't collide with this particular pedestrian. Cool. And what is more important is that, for any of these systems, it's not sufficient to just test them in open loop, meaning did they do something similar to what a human do? But you need to test them in closed loop, which is now the importance of the simulator, such that you really see whether, as you execute the maneuver that you intended, you start with having problems of what's called compound errors, because the small deviations might actually, end up in a very, very, safety critical cases and issues in your system. Okay, so in closed loop, metrics are actually extremely significant. This uses the Waymo prediction system, followed by one of the best planners out there. And this is, the end-to-end system. And you see that, it's much, this is like very difficult scenarios in the simulator. So it's much safer, it's smoother, and in progress better. Okay, this is when you really see the difference between the planners. So it's a much better way to actually build autonomy systems. All right, so I actually, quick time check. How many minutes left do I have?
Well, I mean,
oh, sorry.
Go ahead, Jesse. Oh, okay. Yeah, just want to say maybe another 5 minutes or so,
5 minutes.
and then we should go into questions. Yeah.
Fantastic, fantastic. So I will just show you the highlights of the simulator. So let's go over it. Right. So maybe actually let me just go over here. So if you look at the approaches in industry with respect to simulation, what is important to note is that in closed loop simulator, the only thing that they really test is the motion planner. So they build simulations that are bounding boxes and trajectories represented in scenarios, and then they basically say, okay, how, they roll out the motion plans and then see whether the planner does actually something wrong. So there is, a couple of problems with this. The first problem is that you're only testing one part of the software stack. So you don't, even if you do very well, you have no idea whether your system will work in the real world because, you don't know how the perception and prediction system will actually react or what are the errors, right? And at the same time, typically this is, ground truth or very simplistic noise. So even the motion planner, you're not even testing that actually that bit is actually correct. So you need something else. We need something that you can really simulate the sensors at the scale with all the long tails, etc., of how the scenes might look like, how the actors might react, etc., such that you can test the entire software stack. And you need to do it in a way that mathematically what happens in the simulator really correlates with what happens in the real world. Okay, so if you want to do such a, this is the next generation of simulator that doesn't, companies don't have such a simulator, but it's a must for self-driving. You need 3 pieces. You need to generate the virtual worlds, you need to generate the scenarios, and then you need to basically simulate how the sensors will have observed the scene. Okay, so very quickly, let me show you how we actually do these 3 things. So for virtual worlds, the way that the industry does this is by using artists to generate, CAD models of, vehicles and the scenes, etc. And they use very simple automation like procedural modeling to compose this into bigger worlds. So this is not realistic, and it's also, not something that has the diversity of the real world. Our approach is very different. So what we do with our simulator is that, we drive around the world, and then every single area that we have driven, we can reconstruct it like with very, very high fidelity. Every single actor that we observe, we can reconstruct it as well in 3D with texture, for example, the vehicles. And every single pedestrian we have observed, we can also automatically reconstruct it in a way that we can reanimate it to do any action that we want, right? So this is a game changer. You want from artists that are very expensive and very hard to do something to an AI system that can see the world and then basically recreate everything such that now you can build different worlds by placing all your actors in these backgrounds, right? Doing specific scenarios. So this is what it really gives you the scale and the level of realism. Oops, sorry about that. I was too optimistic. The next thing that you need is to be able to simulate the behaviors of the actors, right? And in particular, what we do here is that, so the industry uses, again, very simplistic ways to do this, mostly like rule-based or procedural modeling. Here we use multi-agent AI systems to do this. And here what I'm showing you is when unroll, this is all simulations. And you see that, taking into account all the interactions between all these different actors. So it actually works really, really well, can generate, generates very realistic scenes. And what is important is that we can also create some of these behaviors that are more rare in a way that are very naturalistic. In this case, right, is creating a U-turn for this particular vehicle. This is our multi-agent simulation, right? Unrolling into the future. This is lane changes, right? And we are simulating everybody in the scene at once. Okay, and unprotected lefts, like in this case, for example. All right, so we have this way to generate long tails of the distribution of our behaviors in a super, super realistic manner. Okay. Sorry about that. And the last bit that we need is to be able to render the scene. So basically, this is where the sensor simulation comes. So we have the virtual worlds, we have the actors performing stuff, and then we need to generate how the vehicle will have observed the scene. Okay, so here is the real world. This is the LiDAR simulator. And you see that are very, very similar, but it's more important for the perception system, which is its output is in green. It basically behaves the same way in simulation or in real, right? This is why you can really correlate that this software stack will do the same. And this is very, very important and a game changer. And then basically we can piece this together and create simulations, right? In this case, we are creating a safety critical case, and we have the entire software stack that, the input is the sensor data that is reacting to this actor in particular, right? And you can create this at scale, right? You can create billions of these scenarios in all these different locations with variations. All right, and last video is that you can do the same thing for other sensors. This is cameras. And what I'm showing you here is twice every video, and for every video there is a few vehicles that are actually fake, were never there in the first place. And your goal is to detect which ones are. It's like the Turing test. And in many of these scenarios, it's actually really hard to say which ones are fake versus not. For example, this car in front of us is fake. It's in 3D, it has very realistic dynamics. This car here is also fake. You will not have seen that, right? So this is sort of the super high fidelity simulation that we have. Cool. So, and what this simulation allows you is to really drive. No need to drive in the real world. Instead, you can test the system and train the system in simulation. Okay. So just to summarize, right? The promise of self-driving, right, is a promise of really of a better world. There is so much benefits of this technology, and we just need really the right technology to solve this, and we can solve it. There is no question about it. Now, the other thing that is, as I mentioned, important is that we need to, do this by looking at diverse perspectives and diverse sort of technology, right, in order to build the best technology. So we need to build diverse teams, and these. 7 months ago, I guess I started Wabi to really, focus on or deliver this vision. And I was joined by an incredible team. We are, 40 plus and growing very significantly, right? We raised $100 million in 2 months, which is, I think, is the second largest Canadian Series A in history. We have all it takes now. We just need to focus on execution, and there is so much that brilliant people like you can contribute into really, bringing self-driving to reality. So thank you for listening. And this is all for me.
All right, wonderful. Thank you so much. We've got lots of questions. So the plan is to go until 2 and just cover as many questions as possible. I started to collate some of these questions, so cluster them. So maybe we could just start with these clusters. So I guess the first question is, how do you ensure that intermediate representations are interpretable? And there's also a related question to how do you do this also for graph neural networks?
Yeah. So I guess there is not a precise definition of interpretability, right? And what we are after with interpretability is twofold. We want something where, we need to explain the decisions that the self-driving car makes and be able to trace into why it makes those decisions. And also the interpretability, we also like interpretability in the context of we want to build our intuitions and our prior knowledge of the task at hand. So one way to actually do this is through these representations that mean something to us. And I believe that also these interpretable representations serve as bottleneck that help you with generalization afterwards. Now there is still a debate, right, into what interpretability means or not, and it ties to verification. And I'm more than happy to debate for hours on this. But basically, when I'm talking about interpretability today, I'm doing a little bit loose way, and that's basically what I mean.
Right, but I guess I guess the challenge is in sort of your very premise of the architecture is that you allow these wide interfaces and potentially latent features that just discovered and used by the system, and that's sort of at odds, I believe, with the interpretability at all times and being able to actually account the system for how it makes decisions. And I guess that's a challenge that perhaps it's something that still needs to be addressed within. Like that.
And if you look at for example, the more sophisticated prediction model I showed you, right? So it's actually a conditional BAE where the encoder and decoder are graph neural networks where the latent space kind of tries to represent the scene itself, where the representation of the nodes really encode actors. So there is certain sort of like injection that prior knowledge, but I agree definitely with you that there is a lot more to be done on this.
So perhaps there should be human in the loop. I mean, that's what I like to see in future. But anyway, so the next cluster is related to sort of the long tail, right? So questions like, how do we take care of the long tail in motion forecasting, for example? Also, ML is great at interpolating, but often fails to extrapolate. And in that long tail, you have things like human road user errors, behaviors that you have not observed yet in the field. And so, a purely data-driven approach cannot possibly extrapolate to these cases. So how do you deal with that?
Let's see, great question. So in terms of interpolation versus extrapolation, just focusing or building the system just from real data is not going to solve it, right? You need something where you utilize miles driven on the wall and whatnot, but you also can create additionally things that happen, right? This is where the simulator is very, very important. And in particular, it's not about creating a fixed set of scenarios. It's also very important to be able to modify those scenarios in a way that helps learning, whether it's through adversarial stuff or something else, right? We can debate about what is the specific technology to do this, but this is a place where it's very, very important for the simulator. Now, as it relates to the long tails, the other thing that is maybe one of the works that we've done that I didn't mention here is, how do you make sure that when you sample these sync consistent samples, they are actually diverse? And you want them to be diverse, not necessarily with respect to the motion forecasting, but you want to be diverse with respect to the actions that will make you do, right? To make sure that you actually take into account all the potential things that might happen. So there is particular, line of work that is actually very, very exciting, which we will present, I guess, next week at ICCB. We basically injects or has, there's a different sampler that is a diverse sampler, but it's a diverse sampler for the end task. And then uses a different type of planning, which is contingency planner, to actually be able to handle the diversity of all those different explanations in a much better way. And what the contingency planner is that if you look at these motion planning techniques that I show you today, or that you see in the literature, typically what they're after is a full trajectory. Is given all that I know now, give me the trajectory for the next few seconds, and few seconds typically means 5 to 10 seconds. But if you think about how you're actually executing this planner, you are not executing 10 seconds and then doing something. You are actually doing, executing this in a loop where you only execute a small trajectory. Right. So this contingency planner is what it does is that it looks for the short-term trajectory such that no matter what happens in the future, I have a trajectory that is compatible with the shorter trajectory that will be able to solve it, that will be able to be set to drive safe. And this is a very, very powerful type of planner. And that's something that you need as you go into more of the longer long tails.
Right. So kind of defensive driving, if you want, right? In a certain sense, or kind of having...
Yeah, but it's not so defensive in the sense that if you go for the expectation, you will end up being, I guess a bit more defensive, but if you go on the expectation, you end up with something that is super conservative. This is what you will see with self-driving cars, right? Is that they're very slow. They are, they look like, someone that is very cautious, right? And with this type of planner, right, the defensiveness, you can actually play with the length of that trajectory. You end up with something that is much more human-like, without being, safety, problematic for safety. So you end up with, actually, these planners have better safety properties and can imitate humans much better.
Right. So when faced with novel situations, human can essentially rely on many layers of common sense grounding. How do you think, how serious is this absence of that capability in current systems that use AI that doesn't have common sense? Is this a problem?
Yeah, great question. A very, I guess, fashionable question these days, right? With common sense. Yeah, so oftentimes these systems don't have common sense. One of the works that I didn't have time to go in details is, how can we make the system learn common sense? And is there a way to inject that knowledge through, your loss function, such that they actually understand what that common sense is? Or they capture some of that common sense. So this is the kind of line of work that we've been doing is trying to to inject common sense through the learning objective. But definitely humans will have much more common sense, and they will know concepts that a self-driving vehicle will never know. Right? Because humans are doing much more tasks than just driving.
Right. It's the CYC, Lennart CYC system, right? It's doing this for 30 years, trying to encode common sense, right? So.
Yeah, but that doesn't mean that you cannot encode the things that you really, or at least the minimum set of things that you need for being able to do this task. Now, these driving vehicles are superhumans in the sense that they see much better, right? So, but right now, if you look at the standard, a lot of this, straight up neural nets, they definitely lack common sense. They, if you just take, your favorite, ComNet, LSTM, whatever, and use it for prediction, they shoot off the road they collide from time to time. This is why you saw on my metrics, but on the metrics I show. But by incorporating, more and more sophisticated, modeling, then you get better and better at learning some of those common sense concepts. But yeah, definitely an open question.
Yeah. There's another great question here. So the question is knowledge distillation required to ensure that the self-driving car can make safety critical decisions in real time? And I guess, this sort of relates to maybe things that Tesla has been showing in their Tesla AI Day, how they use much more powerful models and ML and physical and all sorts of other models offline versus what they actually put on the car. So what's your take on it?
Yeah. So whether it's required, nobody knows, is a very interesting direction. And there is some of the new stuff that we are doing. I mean, it's not what Tesla is doing, but it's something where we use knowledge distillation. Whether it will be on the final solution, I don't know, but it's a powerful idea. So definitely, you're doing research on this direction. I think there is a lot that you can do in this driving domain.
All right. Well, another question here is, how do you pick the right time horizon for predictions, which can be probably very context dependent?
Great question. So let's see. In systems in the industry, the prediction horizon is fixed to a fixed value, typically. Okay. And the fixed value is tied to the motion planner. And typically the prediction horizon and the motion planning horizon agree, is the same. Unless you have a very sophisticated cost to go in the motion planner that can utilize longer horizon for prediction, but typically this is not the case in the industry. And how you pick it? Typically you pick it based on, it's not something that the developer chooses. It's something that comes out of the constraints of the problem that you intend to see or to solve, which is, what is the horizon you need in order to react to certain things happening? And that's sort of like where the set of, the system engineering, testing, and safety folks will actually give you all those constraints. Okay, and that's basically how this number is typically set. Now for papers, that number is all over the place, right? That's very different. Like when we show papers, we isolate one part of the system, right? It's not the entire system that we show. So typically you will see, some folks doing 1 second in, a long time ago, 3 seconds, 5 seconds. Yeah. Now, if your application, for example, at Waabi, we are doing long haul tracking. So a truck needs a longer time than a vehicle to actually, for example, arrive to a safe stop. So your planning horizon and your prediction horizon is longer. Right. It also depends on your application domain.
Right. Yeah, there's a couple of sort of more general questions. So there's one question about accountability, in particular from the regulator's point of view. Who would be responsible if something goes wrong?
Yeah, I mean, let's see. Let's step back for a second. So I think the one thing that is fair to note or to say is that this field has been very bad at transparency and accountability, meaning that it's been, folks have been sharing, how well their system do, where they have issues, what are the things that are difficult for the systems to do, what are the things that are still, unknowns, etc., etc., etc. So I think there is a need for much more transparency and accountability, and this is something that I intend Waabi to definitely do. And I also think that it's important to showcase the technology from a technical perspective, but also for people to get exposed to it. And I think this is very important for for people to really trust that this technology is safe. Okay, so this relates to the users as well as relates to the regulators. Now, with respect to the regulators, which comes quite interesting here, is that do they have the tools to actually understand whether a particular software stack is safe? The answer is no. And there is, this field is also advancing very fast, and regulations are very lag behind, right? So it's pretty interesting. So, a lot of the technologists, and the regulators, they need to come together, and we need to really expose what this technology is and doesn't, and etc. So they really understand, what this is. And the other thing that is missing is proper metrics. We've seen vanity metrics. Multiple intervention is a vanity metric that doesn't reflect anything, right? So we need a way that, right, like the same as we have for humans, the driving permit. You can argue whether it's sufficient or not, right? But we have a way to at least certify that somebody can do driving, can drive, right? So we need a similar thing for self-driving, and I believe that tools like our simulator have the potential to become, part of that set of things that regulators would utilize to certify systems. But there is a lot to be done on that, and earning trust and transparency, etc. Yeah, great question.
Yeah, so I guess this is very related. So, what type of safety arguments, whether this is anything deductive or including verification methods, or inductive or statistical or just testing based, or is there place for human inspection? So what types of evidence do you think is necessary, should be used for assuring, particularly the AI part of the system?
Yeah. So we need a combination of all those things, right? In order to certify these complex systems, it's not just one type. The one thing that is interesting that we also need people to understand is that the certification that we will have with neural nets will look probabilistic, in my opinion. Will look like, what is the risk of this vehicle in this particular operation domain? And that's something that we also need to educate people to understand what it is. Now, there is a lot of work still that needs to be done in terms of how to build a safety case. Right, and the one thing that is, there is a lot of really exciting work in the, as it relates to robustness, certifiability of neural nets and all that stuff. But there is a big distance of separation between what these great papers in academia are talking about and this real system that you need to certify. And we need to close that gap. But there is a lot to be done there. And if folks here are doing research on this, this is a fundamental part that is still very misunderstood.
Right. All right. Here's a question. So, what is your take on Elon Musk's opinion that one should focus on just camera and not touch LiDAR?
Yeah, so I'm not going to give opinions with respect to a specific competitor, okay? But right. I can tell you about what this approach is and why. So I believe that we should use multiple sensor modalities because, this is a safety critical system, right? And we want the best observations so that we can actually find a solution that is safe. And is it possible to do it just with cameras? The answer is yes, because humans can do it. Therefore, you can, potentially there exists a solution. So it's a matter of finding it. Right? Now, in my opinion, the path to deploying safely this technology lies on multiple sensors, including LiDAR. LiDAR gives you, very good geometric cues, which are very, very fundamental for safety in self-driving. So no, we will not be doing just camera-based. And I am a computer vision person, right? And when I was an academic, I used to say, no LiDAR here, no LiDAR there. When I joined industry, I understood the difference when in academia, we try to solve the hardest problems, and the difference between this and building a robust and safe solution. Right, so multiple sensors, in my opinion, are the way to go.
All right. Another question is about how self-driving cars should be, I guess, behaving in traffic, such as, for example, what level of assertiveness or aggression should they exhibit. A car that's too timid might have trouble making progress, especially in very heavy traffic. So how do you judge that? And
yeah, negotiation is a very, very interesting topic in self-driving. By negotiation, I mean you want to change lanes and there's heavy traffic, or you want to take an exit or merge into something. Right? And it's actually pretty hard problem, right? Because on one side, as humans, oftentimes we declare intent, even if there is no gap, so that people allow us to pass. And Ryan, it's very, very hard to do that with a self-driving vehicle. It's very hard to understand what is the amount of burden we are putting on everybody else and whether it's the right maneuver. So there is, I guess, this new line of research on, it's called sometimes reactive planning, prediction condition on planning, etc. So this is, it's just touching the surface now. It's really starting, and it is a very, very important component. So we want a solution where we are predictable, because we're gonna interface with humans for a very long time, and we are safe, but we also need to make progress. So there is a delicate boundary there. And I was mentioning before that these contingency planning methods are actually really, really interesting for this kind of thing, but it's very, very hard to do. Okay, so there's still a lot to be done there. Like, you don't want self-driving vehicles that are super conservative, because also humans start behaving differently, and then you end up with situations that you don't want to get. Great question.
Right. Okay, great. I think we will be wrapping up. So maybe just one final question. And I think it's a good question for the end. What do you think is the sort of single biggest barrier or obstacle to advancing this technology that needs to be addressed? Whether it's in terms of number of data or specific technical problems to be solved. What do you think is the bottleneck today?
Yeah, so as as maybe I mentioned, two, right? And this is how Wabi kind of is structured, right? So there is autonomous system that can handle the long tails. That's the first level of difficulty, and high fidelity closed loop simulator that can test that software stack and can also train it to handle all those long tails. We need the two. We cannot separate them, and we need the next generation of these two. And that's basically where the next couple of years are going to look like.
Sounds great. Well, thank you so much for a wonderful talk and great discussion. And I'm going to virtually clap for everyone here. Thank you so much.